Now student, today we are going to see the induced EMF in the stationary coil. Yesterday we have seen that is magnetic field is uniform and your conductor will be in the moving stage. That we have seen yesterday, right? You have seen by cross line we have shown the magnetic field, then we have considered one A, B, C, D as a coil, and that CD conductor is in the motion. Means what? In previous lecture we have seen the EMF induced when conductor is in the motion in the uniform magnetic field. Now in the today's lecture we are going to consider EMF is get induced in the coil magnet experiment when coil is stationary and magnet is in the motion. Now what that experiment is there? Just concentrate on it like that. In this diagram, I am getting this semicircular arch. This semicircular arch frame is made up of aluminium and it is fixed with the help of this M1 and M2 as a support. Then at the center of this semicircular arch is of radius 50 cm. Here at the center there is a pivot. From pivot I have considered the magnet which will be in the hanging stage and the another connection will be given to the center of this arch. Now what the thing is happening here, how the magnet is in the moving, when this semicircular arch will set into oscillation. So this semicircular, only this upper part is fixed, not a complete upper part, only this arch will be fixed through M1 and M2. Therefore, when I am going to give the oscillation to this semicircular arch, this magnet will set into the motion. So now, when this magnet will set into the motion, the magnet will get entered inside this coil. Now this coil has a larger area, so that magnet can safely go inside the coil and it will safely come out from the coil without disturbing the coil. Now this coil has 1000 turns. This coil is furthermore is connected to the circuit, so that here when the magnet is in the motion, there will be change in the magnetic flux inside the coil, and due to that change in magnetic flux inside the coil, EMF will get induced, and that EMF reading you will get it on this voltmeter, and through that EMF also we can charge a current, we can charge a capacitor. And that charging current you will get it on the ammeter. So in the textbook, these two circuits they have shown separately. But to explain that, I have connected it together. So to the coil, this circuit is connected, and this part, semicircular arch, is going to be set into oscillation. So this is nothing but your coil magnet experiment. Now here what happens when this magnet, now initially the magnet will be considered at some location on the semicircular arch, and the central part of the coil will be given by this reference line. So the central part of the coil and magnet, there will be certain angle theta. Initially magnet and coil both are at the rest position. So theta is 0. Rest position means what? There will be no change in magnetic flux, so EMF will not get introduced. But now, when this semicircular arch will start oscillating, this magnet will come inside the magnet, inside the coil. So when this magnet will come inside the coil, there will be a change in magnetic flux. So when magnet will come inside the coil means what? Magnet is rapidly coming towards the coil. So when magnet will come rapidly towards the coil, there will be a faster change in the magnetic flux. And if the magnetic flux change is faster, automatically the EMF induced will be greater. And when that coil will again swing back, the magnet will move away from the coil. When that magnet will go far away from the coil, then there will be a decrease in the magnetic flux. And that decrease in magnetic flux gives us the decrease in the induced EMF. So two cases. One is magnet will be rapidly coming towards the coil, faster change in the magnetic flux, EMF induced inside the coil. When magnet will swing out of the coil. It will go away from the coil slowly. So the change in magnetic flux will be slower in the decreasing order, and therefore change in induced current or production in induced current will also goes on decreasing. So these are the two concepts. Fine. Now that two concepts are explained here on the graph. In the graph you are getting this curve portion B, C, this part D, and here is the E. In that this CD portion is a flat portion of the graph. This flat portion means what? During that the this magnetic field will remain constant. Now when magnetic field will remain constant, when this bar magnet will come inside the coil, remain inside the coil to the mean position, at that time the magnetic field will remain constant. So that constant magnetic field will be indicated by this flat portion of the graph as I see. And now we can concentrate on this BC part. This BC part, this slope is sharp. This DE part of the graph, again the slope value is sharp. When this slope value you are getting sharp, when the magnet will be coming fasterly at the faster rate, when this aluminum semicircular arch will swing and the magnet will come towards the coil in the faster rate. At that time the change in magnetic flux will be at the faster rate. Therefore this change in magnetic flux is at the faster rate, so the graph slope is sharp. When it will come to the mean position, magnetic field will remain constant. And when that magnet will again come out of the coil, so when the magnet will come out of the coil, so there will be the decrease in the magnetic flux in the faster rate. So that will be given by the graphical curve as a D. So in that manner we can explain the change in magnetic flux inside the coil. Now due to that change in magnetic flux, there will be the production of EMF. Now we are knowing that according to Lee's law, EMF is equal to nothing but minus d phi by dt. Right? Now here, this BC part, what it will indicate? BC part indicates that magnet will be coming rapidly towards the coil in the faster speed. Therefore, there will be a faster increase in the magnetic flux. Magnetic flux will goes on increasing, means phi is positive. Phi is positive, but Lee's law says that EMF is equal to minus d phi by dt. Therefore, EMF is negative. So here we are getting at the time interval t1, when the phi increases at the faster rate, at that time interval EMF introduced is in the negative direction. Then when magnet will be moving away from the coil, at that time the magnetic flux will goes on decreasing. So see here, the E part will be shows a decrease in magnetic flux. Magnetic flux decreases means in the negative sense. So negative will become positive. So for time interval t2, when the magnetic flux decreases, your EMF will become positive. So here I am getting in half oscillation, I am getting the negative pulse as well as the positive pulse. And when next half oscillation will be there, again I am getting one negative pulse and one negative positive pulse. See here, coil magnet will be coming towards the coil, negative pulse, moving away from the coil, positive pulse, again coming towards the coil, negative pulse, again going away from the coil, positive pulse. So like that manner there will be a generation of EMF. Now this EMF generated E, according to Lee's law, we have written this. But now this EMF introduced will be dependent on this theta value. Therefore, I can write down this E is equal to minus d phi by d theta multiplied by d theta by d theta. Theta is what? Angle between the magnet. Now what is the thing here? When the magnet will be at the mean position, theta value is 0. Theta value is 0 degree means what? Magnetic flux introduced is maximum, indicated by CD portion. Magnetic flux is constant, magnetic flux is maximum, theta is 0, therefore EMF will reduce to that of 0. Because what? Theta is 0. Theta is 0 means what? D theta by dt. That will reduce to 0. 0 multiplied by this factor. So EMF will be 0. So now your EMF value will be totally dependent on this factor, that is d theta by dt. In that, this theta is to be called as a oscillation amplitude. Oscillation amplitude means what? Whatever this magnet is oscillating with respect to theta. So this theta is to be called as the amplitude of oscillation, which will be given by theta is equal to theta 0 sine of 2 pi capital T upon small. Now I can differentiate this. So this d theta by dt can be written as theta 0 is the peak amplitude, then differentiation of this sine 2 pi capital T upon small t, which will be written as cos of 2 pi capital T, small t upon capital T into this term, which is equal to nothing but 2 pi upon t. Right? So now what I write down? This constant term I take it here. So 2 pi theta 0 upon capital T into cos of 2 pi small t upon capital. This is nothing but your value of d theta by dt. Now this value of d theta by dt I can substitute in the EMF equation. So your EMF equation is what? Minus d phi by d theta into this value is here, which is that 2 pi capital T upon theta 0. Sorry, I have written because 2 pi theta 0 upon capital T into cos of 2 pi small t upon capital. Now what I want? EMF should be maximum. When I get EMF maximum? When this cos term will reduces to 1 and this cos term will reduces to 1 when this term cos angle will become 0. So this cos term, that is 2 pi small t upon capital T, will become 1. At that time your EMF E, which is equal to nothing but minus d phi by d theta into 2 pi theta 0 upon t. At that time, I am getting this EMF value will become maximum. EMF value maximum means what? This is maximum value. Means what? This term will be reduces to peak value of EMF. Peak value of EMF E0 is equal to what? 2 pi theta 0 upon. Right? This is nothing but as your peak EMF. Means what I can say that your EMF introduced inside this stationary coil due to moving magnet is directly proportional to the theta 0, that is amplitude of oscillation, and inversely proportional to the peak. So this is nothing but as your coil and magnet